right, we are at 4:45, and so I know that I am what stands between you and beer. I'm acutely aware of this fact, so I promise not to keep you late. But hopefully you'll learn some cool stuff in the meantime. My name's Scott Fincher. I'm a data scientist for KNIME. What does data scientist mean? It means, for me anyway, I'm on the education and evangelism team with KNIME. How many of you have heard of KNIME? 1, 2, okay, good. That's not uncommon. We're a European company. Most of our staff are based in Germany. We've only had a US presence now for 24 months or so. So I'm not surprised to see that, but I always like to ask. Sometimes I'm pleasantly surprised. A lot of people know who we are. KNIME is a company that makes machine learning software. It's open source, free to download, and GUI-based. So you can train your random forest model on some data that you've ingested and transformed, all without writing any code. If you want to write some code, that's okay. You can still do that, even within our tool. But that's what we are and what we do. I'll show you a little bit more about KNIME in the middle of the presentation. I won't go too much into the marketing side of that. What I really want to talk about today is what we're calling the creative side of AI, the creative side of artificial intelligence, specifically product name generation. So what we'll talk about, the problem, we're going to have a little bit of an artificially contrived problem here, where we have some marketing team that has been tasked with coming up with some product names, and they're stumped and they don't know what to do. So we're going to build a model to help them do that more effectively. In particular, we're going to talk about recurrent neural networks and LSTMs, how we can build those within KNIME and deploy them. Because of the way these models work, we need to do some transformation on our model inputs, so we'll talk a little bit about sequencing and encoding, and then we'll stop with the theory at that point, just about the time when you start to fall asleep. And then we'll shift over to a demo, which is maybe a little more interesting. I'll show you how we can build deep learning models like this using KNIME, and then how we can deploy it and actually generate these product names and what they'll look like. And then finally, I'll give you some resources. One of the nice things about being a company that provides free open source software is everything that I say to you today, you don't have to believe me. You can just go download our software, try it out for yourself, run it on your local laptop, put it up in the cloud, and produce all this stuff using workflow and data that we'll give you. So don't believe what I say. It's the proof is in the pudding. Go download KNIME and try it out. And then at the end, we've got a couple of freebies for you, some books that you can download if you're interested in learning more about KNIME and how we do what we do. Okay, so we'll get started. The problem here, the idea well has run dry. We can think of our poor marketing team who has been banished to a windowless basement, and they're beating their heads against the brick wall because they can't come up with new product names. That's their only job. They can't do it, and they're stuck. So these poor schlubs sitting in the basement, what can we do to help them out? So I actually feel sympathy for these people because I would have a hard time coming up with new and interesting product names. Anything that I think of is probably going to have been thought of before by somebody who's better at this than me. So naming these products is not as easy as it might sound unless you're already in marketing. So what if there's a way we can help this process along using AI? We often think about AI as something that will help us automate tasks, do something that's repetitive over and over, or maybe we can use AI to predict outcomes from a data set. But we don't always necessarily associate it with creativity. And if you've ever done anything that is essentially a creative task, sitting down and trying to write a song on your guitar, or write a poem, or maybe you're trying to draw something in a new way, a lot of times it's just not happening, right? The creative process can be tedious and repetitive. So we can use that nature of the fact that it is tedious and repetitive. Maybe we can bring AI in there and help us solve the problem. So again, we're going to have this example. Let's say that we're going to help out the marketing team, and this marketing team is trying to generate product names for, we'll say, an outdoor clothing line. So maybe they want to come up with a new name for a jacket, or a backpack, or a tent, or I don't know, something like that. What do they need? What do our marketing folks need? They need the names to stand out. They need to be distinct. They need to be new. It needs to be something that has a familiar ring to customers so that when people hear it, they can actually remember what it is. That's the whole point of marketing, right? It should be something that's fresh and not closely associated with another product. So the last thing we want is to come up with a product name that somehow evokes our competitor's product. That would be horrible and instantly get us fired. we would like, in this particular case, since it's an outdoor clothing line, to evoke the feeling of nature. So we hear this product name and we want to think, I'm standing under a waterfall in Colorado with pine trees and it smells great. You know, I hear this name, I want to have a thought in my mind of outdoor mountain activity. And then on a more practical level, we actually need several potential names to evaluate with our team. A lot of the names that we generate either on our own or using AI are probably going to be not good enough. Some of them will be terrible. So to offset that, let's generate a whole lot of names, and then we can pick the cream of the crop, the top 5 or 10%, and actually set those aside and say, okay, these are good candidates. So practically speaking, what can we do? So what we're going to do is build a model to generate fictional mountain names that don't currently exist based on mountain names that do exist. So as a quick sneak preview of where we're going, take a look at these 3 sets of mountain names, 1, 2, and 3 in the little boxes. Which one of these sets of mountain names do you think are real? Just from glancing at it. Ha! I fooled you. Maybe I didn't. None of those are real. They're all fake. I mean, some of them sound good to me. A Casterland Mountain, I would buy a jacket that said Casterland on it, or maybe even Little Buck Butte. But those are all generated by the algorithm that we're going to talk about how to build today. How do we actually go about doing this? So as I mentioned before, we're going to build a recurrent neural network, an RNN. More specifically, we're going to look at what's called an LSTM, a long short-term memory network. And that network is going to have a many-to-many input sequence. I'll actually define what all of that means here in a minute. And then we're going to train the model using our software, NIME Analytics Platform, and we're going to deploy it in a bunch of different ways. So we'll use a proof of concept that we've built out using SageMaker. We can also stand up what's called a NIME server within AWS Marketplace and deploy it that way. Yeah, we'll get into that in a little bit. But first, before we actually talk about what are our mountain names going to look like, let's talk about some theory. So what are RNNs and what are LSTMs? How many of you are familiar with recurrent neural networks? So like maybe 20, 30% of you. How many of you have actually used them in deployment? So a little bit fewer. Okay, for you guys, this next section is going to be stuff you already know. Apologies for that. But for those of you who have never seen this before, I'll give you 10 or 12 minutes or so, just a rundown of what these things are and conceptually how they work. So RNNs are a family of neural networks that are used in particular to process sequential data. I've got this little figure down here. We'll talk about specifically what that is in a second. Here's the key thing to remember about RNNs. Okay? They're going to allow for persistence of information. What is persistence of information? It's kind of like memory, right? These models sort of have a primitive type of memory. It's not perfect. It doesn't necessarily go back all that far in the sequence, but it is there, and it's why they're useful to us in doing these predictions. What are RNNs used for? All sorts of different things. So text generation, which is what we're going to do today. You can even generate images with RNN, which is kind of funny. In fact, a lot of the stuff that you can do with RNNs is kind of funny. You can do image captioning. Given an image as input, give me a string of characters that defines what that image is. Language translation, I want to go from English to German or German to French. I could do that with an RNN. Any sort of numerical time series formatted data, even music, you could look at using RNNs. Sensor data is another example. So this is the kind of stuff we would use RNNs for. What I'm showing here at the bottom in this diagram, and this is not my diagram, this is from Christopher Olah, who has a really good blog post on RNNs that you can, I'll provide a link for that in the slides if you'd like to go read about it later. What's going on in this diagram? So let's look at just what's on the left-hand side here of the equals sign. So we have some, at the bottom, we're going to go from bottom to top when we look at this. We have some input at x sub t. X is our input in the blue circle, and t represents some particular time step, okay? Our output is going to be the purple circle at the top, h, again at some time step, so h sub t. And what's going on in the middle is our neural network, the green box with the a on it. And the loop that goes around the little green box there indicates a type of repetition. So the network, at each step, it runs sequentially, is going to be fed not only the input x that we give it, but also a copy of the neural network from the preceding step. So it's a little bit easier maybe to understand if you look at the right-hand side of the diagram now. You can see what we call an unrolled version of the network. So this is exactly the same thing, it's just a different way of representing the concept. So now instead of having this loop that goes around the green box, we have several different copies of the green box, and we can see each individual time step represented along the way. So we have starting with x sub 0, which feeds into x sub 1, or, well, it doesn't feed into x sub 1. X sub 0 feeds into the model associated with x sub 1, and all the way down the line until we get to the end of our sequence. So each copy of this network works on a single step of the input, but a key thing to remember is that every time you see the green A, it's still the same network. If you know anything about neural networks, it actually has the same weights at each step. One thing we will not talk about is how the training is performed here. There's a whole bunch of math that goes into how this works. It uses a technique called backpropagation, and in particular with RNNs, it uses something called backpropagation through time until the model converges. Just in the interest of time, we won't talk about that, but there's a whole bunch of stuff out on the internet, and then some of the slides I'll give you at the end where you can learn more if you want to find out about backpropagation. So RNNs, as I mentioned, have a type of memory, but this memory is somewhat flawed and quickly hits a point where it doesn't help us produce useful results when we're doing predictions with it. So what are some of the limitations of RNNs? They have a simpler layer structure when compared to LSTMs, which is what we're going to talk about in a second. You can think about, as an example, what's going on inside the green box with the A on it. Maybe if I have a really simple RNN, all I have is a single hyperbolic tangent or tanh layer. Maybe that's all that I have going on. That's not actually that much. So, and it may be more complex than that, but generally it's going to be simpler. So because of this simpler way that the RNNs are constructed, the memory is sometimes too limited to be useful. So here's another example. If we think about the words in a sentence being fed in sequentially to an RNN, we could have a short sentence like cars drive on the road, highway, freeway, whatever. It's actually in our kind of contrived example here, it would be easier for the model to pick up on the fact that it's going to predict the word road because it only has to look back just a few steps in the sequence to see the subject, cars. It doesn't have to go back that far so it can kind of figure that out. Now, something that might be tougher for an RNN is a longer sequence. So you look at the second sentence, I love the beach, my favorite sound is the crashing of the waves. We would be able to figure that out because we are super geniuses compared to RNNs. We can see far back enough in the sequence to realize the context that a beach is going to involve crashing waves as opposed to crashing cars or crashing glass or whatever else. So how can we overcome this potential limitation that an RNN with a simpler structure would have? One way we can do that is to introduce more complexity in the structure. So now you can see in this middle bit here, we have a whole lot more stuff going on. What is all that stuff? Well, when we add complexity in this particular way, we're going to build what's called an LSTM, a long short-term memory network. And really, these are just special types of recurrent neural networks with the more complex structure. The important bit here about what's going on in the LSTM is the cell state. That's this top, can I point? It's the top horizontal line. So what's being fed from each step in the sequence to each next step of the sequence, we have this is what you can think of as the memory, that top horizontal line. What governs what gets fed into the cell state? There are a few different things going on here. So we have different gates, and the gates are represented by the little yellow boxes. It's easiest to think of them as being 3 gates. So a forget gate, an input gate, and an output gate. These are typically sigmoid functions. What do these represent? So let's again think of an example of a sentence where we're feeding words sequentially. This is not exactly how our LSTM is going to work that we build, but just for the purposes of kind of illustrating how they work. The example of what might happen in a forget gate. Maybe in a previous part of my sentence, I had a subject that was female. And now I've introduced a new subject that is male in the sentence. And so what I'd like to do is forget the previous subject so that I can get the pronouns correct further down the line. So a forget gate could help me do something like that. The input gate is just going to take in whatever we have from the x sub t at the bottom, feed that new information in. And then the output is going to govern what gets passed onto the cell state. So the output gate might be something like, hey, maybe we just saw a new subject introduced. Because we saw that, maybe we should prepare for a verb. Or maybe something a little more concrete where at some point in the preceding sequence we had an open parenthesis. So now we would like to be looking for a good time to have a closed parenthesis. That's something that maybe the output gate could help us govern as far as what gets passed to the cell state. This is super simplified, and I'm going through this kind of fast, I know. So again, I'll provide some links at the end if you want to get into the details of really how this works. What you see in the little pink circles here are all fun matrix operations like matrix addition and dot products and cross products and whatnot that actually take the mathematical structure that's represented, what gets passed out of the gates, and ties all that together. Something important to remember here is that I'm representing this neural network as these series of green boxes, right? But the LSTM that we're building here actually consists of a whole bunch of different neurons. In the one that we're going to build, there'll be 256 neurons within the layer, and each one of those is going to be looking for different patterns. So like I said before, if we saw a subject, let's look for a verb. That might be something that one neuron is doing. Another neuron might be looking for, the closed parenthesis where the open parenthesis came before, things like that. There's all sorts of things that these neurons could be looking for that the model kind of, we don't necessarily explicitly tell the model what we're doing there. The model kind of figures that out along the way. Okay, so we've talked about the model structure and sort of how that works. Let's step back again and think of our mountain example, okay? We're trying to generate new mountain names that are fictional, that don't exist, based on mountain names that do exist. And so to feed this information into our neural network, our LSTM that we're building, we have to format the data in a particular way. So let's talk about that. So where's the data coming from? How can we feed it to our model? So in this particular case, we took roughly 33,000 names of mountains in the United States. We just ran a Wikidata query on Wikipedia to pull a bunch of those out. And you can see, I think this is the top 11 here that came out. White Butte, Belknap Crater, these are all real places. Maybe you've been to some of them. So we have to figure out a way that we can take these sequences of characters and feed them into the model in such a way that the model can understand them and do something with them. So we're going to use what's called a many-to-many input sequence, and each individual character in the words is going to be a time step. So what you're seeing on the bottom right-hand corner there is a diagram. It's basically just the same diagram as what I showed you before, except now, instead of x sub t and h sub t, we actually have real characters. So, given a start token, if we want to, you can read across the top that says Red Hill, some mountain name, right? So what we want to train our model to do is, given a start token, predict a capital R. And then at the next step, given a capital R, predict a lowercase e, then predict a lowercase d, and so forth, all the way down the line until we actually spell Red Hill. That's what we're trying to do here. Let me make a quick detour and talk about the different input sequences that we could use, just because I think it's useful to think about in a particular way. We're using many-to-many, which is on the far right side. There's other ways, if we were going to set up an LSTM, that we could have our input sequence fed in, depending on what it is that we're trying to do. So if we had a one-to-one sequence, for example, you can see that on the left-hand side. An example of what that might be would be image classification. So we have some particular image that's coming into our model, and we would like to classify that as what it is. So maybe I have dog, ball, cat, umbrella. I would like my model to be able to identify what those things are and then classify, D, B, C, U, right? Just one-to-one. One-to-many is a little bit more complicated version of that, where again, I feed in the image, but instead of doing a classification, now I want the model to actually spit out a caption for me, character by character. So actually spell out for me, oh, it saw a dog, okay, it's going to spell out D-O-G. Okay, that's a one-to-many sequence type. Many-to-one is kind of the inverse of that. Maybe here an example would be sentiment classification. So somebody goes on Amazon and writes a review of, I don't know, mouthwash, okay? This mouthwash tasted like gasoline, and I felt like I was going to die. We read that sequence in, and as a result, we get a single classification, very bad, okay? Maybe it's very good, maybe it's excellent, maybe it's average. We could have different classifications associated with the sequence that we feed into the model. And then finally, many-to-many, which is what we're going to be doing here with building these mountain names. This could also be used for text translation, for example. So quick aside, just to give you an idea, when I say many-to-many, this is what I mean, but there are other ways to do it depending on your use case. Okay, data transformation. So we have our mountain names. We have them in some readable format for human eyes where we can look and see, Mount Grable or whatever. That means something to us, but the problem is our neural network doesn't operate on these characters. It operates on numbers. So we need to figure out some way to represent these characters in matrix space. So how can we do that? What we can do is we can convert each one of our characters to a one-hot vector and then feed those vectors into the model so that the model can then interpret it. So at the very beginning, we'll have to apply a simple transformation would be we need to have an arbitrarily chosen start and end token. So in this case, we can say our start token is just 1, 0, 0, 0, 0, 0, 0, whatever. Our end token could be 0, 0, 0, 0, 1. It doesn't matter what they are so long as we're consistent with what the start and end tokens represent. And then meanwhile, you can see, and it might be a little bit hard to see here, in this diagram, we've chosen, capital R would be represented as 0, 1, 0, 0. All of the individual characters will be encoded in this one-hot vector format. A couple other things we need to do. It turns out that the longest mountain name in our input data set has 58 characters. That's fine, it's not a problem, but we need to have all of our input mountain names have that same length so that the neural network can process things appropriately. So for anything that's shorter than 58 characters, which is going to be almost everything, we need to pad out those links, those sequences with zeros. So we do that. And then finally, we need to create a dictionary to be able to go from human readable space to vector space so that the model can do its thing, but also we want to be able to go back from vector space to human readable space so when we get the output from the model, it's just not a series of vectors, right? We want to be able to read these new mountain names we've generated. So early on, we create a dictionary and we set that aside. Okay, we have workflows that I will show you to actually do this, to build the models, to do the transformation of the data, all of that sort of stuff. Let me take a few slides here, just 4 or 5, to talk about KNIME, because when I show you the workflows later, I actually kind of want you to be able to follow along with me as I go through them. And if you've never seen KNIME before, that might be hard for you to do. So just briefly, a few minutes here. What is KNIME? This is what our interface looks like for the KNIME analytics platform. So if you're falling asleep right now and you would rather play around with software, I don't blame you. Just go to knime.com and click the yellow download button. You can download this on your local machine, and this is what it would look like. So we have these individual colored boxes, which are called nodes. Each one of those nodes performs a particular function. So what you can see on the screen here is we have on the left-hand side, the workflows go from left to right. We're reading in some data with the orange node. We have some visualizations that we do with the blue nodes. And in this particular case, we're building a random forest to do some sort of classification task. So we would do some partitioning on the data to split our data into training and a test set. We'll build the model based on the training set. We'll do predictions using the test set, and then we have some nodes to evaluate how the model did, like the scorer node there. We could generate a ROC curve, for example, and then do some additional visualizations at the end. And then because every good data scientist loves to see visualizations of the iris data set, I just love it so much. There it is. Okay, I won't make you look at that for very long. So this part's important for what we're going to get to in a minute. As I mentioned, we're flowing from left to right in our workflow. Each node performs a task on a data. So in this case, the partitioning node is going to split our data set that's coming in from the left-hand side into 2 output sets. And then below each node, we have this little traffic light that indicates to you whether the node has processed or not, whether it's been configured or not, or, God forbid, there's been a terrible mistake. We'll show you that as well. And then, as I showed before, kind of on the previous slide, we take all of these different nodes together. If you're a good data scientist, you put comments in your code. If you're a good KNIME data scientist, you label your nodes. That'll actually, tell you what all the nodes are doing, build some model, train, test, and validate it. We have a whole bunch of different nodes, over 2,000 different nodes that do a bunch of different things. So if you look on the left-hand side there, we have some nodes for data access. This is for ingesting simple things like flat files on your local machine, Excel files, all the way up through reading in data from social media or pulling in JSON. And then we even have big data connectors if you have information in Hive, Impala, Hadoop, you want to do Spark, MLlib sort of stuff. You can do all of that using those nodes. Transformation nodes in the middle there are in yellow. Those are nodes that perform some sort of transformation on your data. So joining, concatenation, partitioning, those sorts of things. Nodes in green, in the middle green section there, are our data mining nodes. So we have all sorts of algorithms for all sorts of different tasks. So all the way from simple things like building a decision tree or linear regression, all the way up through building neural networks and deep learning for image classification or NLP, a bunch of different use cases we support. The blue nodes there are for visualization. So we have all types of different things for simple charts like bar charts and line plots and whatnot. Tag clouds if you're doing text analysis. There's a bunch there. And then finally, deployment on the far right-hand side. What do I actually do with my model once I build it? I could write out an automated report. I could generate some PML and send a model to some other workflow to use. Write out to a database. There's a bunch of different stuff we could do. And then finally, I promise the marketing stuff is almost over. The question that we get all the time is, you're a free open source company that makes software. How do you make any money? Well, we actually have two products. So there's the KNIME Analytics Platform, which I mentioned you can go and download right now. It offers a ton of functionality. And then we also have the KNIME Server. That's our commercial product, and that's what keeps the lights on for us. So the KNIME Server is going to allow you, if you have a team of data scientists, for those guys to collaborate together more effectively. Also, if you need to automate your workflows, you schedule them for overnight execution or whatever. And we have a bunch of different ways to deploy models using the KNIME server. So that's how we pay the bills, is on that side. Everything that not everything I'm going to show you today is an analytics platform. Most of it is, but I'll show you a little bit of server as well. OK, so now that you've actually seen, here's a workflow, here's generally how things flow from left to right, I can actually talk about the specific workflows that we built to come up with these LSTMs for mountain name generation. So let's talk about the structure of the workflow. I have just a static picture here, but I'll open the software in a minute and kind of go through this again. What is this model training workflow going to do? So there's a few things that we need to do. Some of this we've talked about already. So we need to read in and transform our input data set, these 33,000 mountain names that we have. We need to transform them into one-hot vectors, build a dictionary, and set that aside. So that's what's happening in this gray pre-processing meta node. There's actually several different nodes inside of that meta node. The other thing The other thing we need to do is to define the structure of our neural network. That's what's happening on the top layer here, where we have a series of different Keras nodes, one for each layer in the network. And then finally, once we've defined that structure, we're going to take it along with the data that we have and feed that into the Keras network learner. I'll show you a little bit how that works. After we've trained the model, we're going to do a little bit of post-training editing to introduce something called temperature. I'll talk about that in just a minute, a little bit more. And then eventually, we're going to convert our Keras model that we've built to TensorFlow just because it runs faster. And that's what we're actually going to use in model deployment. So neural networks, a code-free approach. Well, it's 95, 99% code-free, as you'll see in a second. So one of the advantages to using KNIME is I don't have to pull up my Jupyter Notebook or write Python or R or anything else. I can just pull the nodes that I need together and have this graphical representation of a Keras neural network. So what do each one of these layers do? If you start on the far left-hand side there, we have a Keras input layer. It's going to define the size of our inputs. So it has this dimension of question mark 95. So the question mark represents the fact that we have variable length sequences coming in, right? All of our different mountain names have different lengths, and we would like to be able to account for that. So we allow for that in our neural network. And then the 95 represents 95 dimensional vectors for the one-hot vectors. So if you think about all the different characters we could have, we have 26 lowercase characters, we have 26 uppercase characters, we have 10 numbers. So we're at 62. And then if you add in a bunch of other punctuation and characters that we're unlikely to use in English, you can eventually get to 95. So that's what that 95 represents. And then we have our LSTM layer. That's the next one. We talked about that. That's where we're actually going to do the sequence analysis. But it's just one layer in the neural network, right? It's not the whole thing. We have a dropout layer in the middle here, which is going to prevent overfitting. In this case, I think we do about a 20% dropout. Basically, what we're saying is take some of the weights in the neural network, take 20% of them basically and set them to 0. Because if that's going to allow for better generalization. We'll get rid of that once we get to the deployment stage. And then we have two dense layers at the very end, one with a linear activation function and one with a softmax activation function. Why do we have two layers there? I'll talk about that in a second. So we've defined this entire structure. We haven't used any code to do it. We've pre-processed our input, and now we can actually train. After we've done the training, then we want to prepare the model for deployment. So this is where we get into talking about temperature. This is just another visual representation of the model. So what's in blue on the left-hand side, that's our input layer. The green box in the middle is our LSTM. The pink is the dense linear layer, and the purple is the dense softmax layer. So we're going to introduce this temperature function via a lambda layer in between the pink and the purple. So what is the temperature parameter? So it has a very particular function. You can think of it as like adding a dial to, maybe an amplifier or something. It gives us a way to control a very particular aspect of what's coming out of our model. So if we have a temperature of less than 1, then we tend to get more conservative or mountainy sounding names that are going to sound better to the human ear. But the downside of that is we also get a lot more repeats. So we get more repeats in terms of the names that we generate, and we get repeats in the sense that the model spits out something that is actually a real mountain name. We don't want either one of those things, so we don't want our model to be too conservative. The opposite side to that is if we set the temperature above 1, that's going to lead to more diverse names. So we're more likely to get something that hasn't ever come up before. Also, we can get some garbage, which would not be great. I don't know of any mountains called TZGX4M2. I mean, maybe on the moon. But we probably don't want those when we're trying to come up with mountain names to sell a product, right? So if we turn up the temperature too high, that's kind of what we get. So we've got to strike a balance. What is the temperature that we need to actually come up with something that's going to be worthwhile for us? So it turns out that the temperature in this case, if you set it to about 0.9, that ends up being pretty good. As I mentioned before, we introduce the temperature using a lambda layer between these two dense layers, and we actually use a little Python snippet node to do that. So this is where, when I say this is completely code-free, it's not entirely true because we don't have a node to do this particular function yet. At some point, I'm sure we will. The use of temperature here is why we actually have these two layers at the end. If we didn't have temperature, we could simplify this and probably just get away with one softmax layer at the end. But using temperature is nice and produces better results, so we did it. Parenthetically, the math is not included here. You won't find any math in any of these slides, which I hope you're grateful for. If you would like to know more about the math that has to do with activation functions or just LSTMs in general, how the different layers of the neural network are tied together, again, that's going to be available in the paper that we have linked at the very end. Okay, let's do a little bit of a demo, and I'll show you the software. And in all likelihood, my computer went to sleep, so that was really smart. So let's try this again. Aha. So this is a NIME Analytics platform. Let me get rid of some of the stuff around the edges so that you can actually see what's going on. Okay, so here is all the stuff that we just talked about in the screenshot from before. In the pre-processing meta node, if I actually double-click and go into this guy, I can see exactly what's happening. So I'm reading in some mountain names. Down here, I have some more meta nodes that are going to create the dictionary and write it out that we talked about. There's just some pre-processing stuff going on. We won't get into the details of everything that's happening here. But what gets spit out of this pre-processing I can actually look at is and it's not too useful to look at it because now it's a series of one-hot vectors that are not actually even fully represented. I can't see all 95 dimensions of them, but KNIME has them in there. So this is what's actually going into the neural network that I'm going to build. So at each step here, I can open up some of the configuration windows. For my input layer, I mentioned that we have this shape of question mark 95, where the question mark represents a variable sequence length, and the 95 is the dimensionality of our one-hot vectors. In the LSTM layer, I can go in and say, hey, first of all, can I even double-click today? There we go. What's nice about setting up the neural network this way is that each step along the way I can see the dimensionality of the input tensor that came from the previous node. So I don't have to remember, I can just see it here. I can set, however many units that we want in our LSTM. In this case, we picked 256. I have information about my activation functions. If I wanted to use particular initializers or regularization, I can set that up here. This is all stuff that normally I would use some Python code to do, but KNIME just makes it a little bit easier to do it via the dialog here. I won't jump through all of these different layers. I'll look at the last one here. This is where we're going to have 95 units in our output layer. The 95, again, corresponds to each of the possible characters that we could be predicting at each step of the sequence. And then our activation function here, softmax, we could choose from all sorts of different things if we want to. Okay, so we've got the network defined, we've got the process data coming in. I'm going to feed this to my Keras network learner, and I won't actually show you the configuration. What I think is more interesting here from a practical standpoint is to look at the learning monitor. So as the model was training, obviously I ran this already because this model takes about 4 hours to run on my local laptop. But if I were running this in real time, I would actually see this accuracy start out very terrible and then gradually increase over time. These numbers would be scrolling by like this, and then after several hours, it's going to reach a point to where my accuracy is 90, 91%, something like that. If instead I wanted to look at loss instead of accuracy, I could do that too. And the nice thing about the learning monitor is this little grayed out button in the bottom left-hand corner. It's going to allow me to stop the training at any point. So this one only took 4 hours. It's not that long. Maybe you have a more complicated use case where you're going to build a neural network that's going to take several days to train, and you would rather not wait for it to train. You'd rather just click the learning stopped button after a few minutes, and then you can build out the rest of your workflow, whatever it is you want to do, using the weights at that point. So when you click learning stopped, it's going to save the weights in the neural network, set those aside, and use those to generate some predictions from the rest of your workflow. Those predictions will probably be pretty terrible, but maybe that's okay because your focus was to build out the rest of your workflow, right? So this allows you to do that. It allows you to quickly prototype and build some toy workflows while still having some predictive ability. Okay, and then I won't cover the rest of these guys. If you want to see how we actually introduced the code, or the Lambda layer via code, this is all here in Python. But you guys can download this workflow and check out exactly how it works. So let me switch back over to slides here for a second. So now that we've actually seen how we're going to train the model using KNIME Analytics Platform, let's talk about some of the different ways that we could deploy it. I show the deployment workflow here. I won't actually go through this in the software because we won't have time. But I want you to see it. Now that we have a model, how do we actually use it? So what this workflow is going to do is just take a single number as an input. The number is going to be how many mountain names do we want to generate? 20, 40, 10,000, whatever. It's going to take that number and it's going to generate start tokens. You remember start tokens from earlier. It's going to generate however many of those we need, along with hidden states for the neural network. And so that's what's represented here by this single guy at the very beginning, this wrapped meta node, where it's going to create the start tokens. And the next thing it'll do is in the next two nodes, the DL network executor and the first care meta node, it's going to use the model to select the first character only of the mountain that we're going to generate according to some probability distribution from the neural network. If we didn't use a probability distribution to generate that first character, then we'd end up with the same name every time potentially, which is lame. We don't want to do that, so we actually want to have some variability, so we pull the probability distribution from the neural network. And then the remainder of what's going on here, you can see between the aqua loop nodes, the recursive loop start and the recursive loop end. It's actually generating the individual characters one step at a time, and each iteration of the loop, if you remember from the rolled out version of the LSTM that we had before, each iteration is based on the previous character along with the previous hidden state of the neural network. So it's going to step, maybe it starts with capital M, and then it generates lowercase o, u, n, t, space, mount, something, something, right? That's how it's actually going to work. So we could run this locally on our own machine. You can do that if you download it, and I did it here. But there are actually some other, maybe more interesting ways to do this. So we have a proof of concept for deploying this model using Amazon SageMaker. So let's say I have a KNIME deployment workflow, the one that I just showed you. I can actually take that workflow and wrap it up in a Docker container along with the KNIME executables, things KNIME needs to actually run. I can take that Docker container and I can upload it to Amazon SageMaker. And so once I'm now in the AWS environment, I'm within SageMaker, and I'll show this in a second, I can configure an endpoint via inference, and that endpoint will allow me to actually talk to the model. So I can call this endpoint, if you look at the right-hand side, via some application. In this case, I'll use a Jupyter Notebook. The call will go to the endpoint will turn around and fire off an EC2 instance that will actually run my workflow for me in real time. And then the workflow results, however many mountain names I requested, will come back, and I'll get them displayed in a variety of ways that I'll show you. So that's one way we could do it via Amazon SageMaker. The other way that we could do it is to deploy via KNIME Server in the AWS Marketplace. So this is our commercial product that I mentioned before. You can go out and spin up an EC2 instance and say, I'd like to use KNIME Server Medium or KNIME Server Large, and have that available to you. So we would take that KNIME deployment workflow and upload it to the server. It's actually quite a bit simpler than like building a Docker container and the SageMaker stuff I showed before. It's basically you just drag and drop it from analytics platform to the server. It's going to be sitting there running on an EC2 instance, and then maybe I have some Amazon API gateway. This is, again, a little bit contrived, right? Why would I need an API gateway to govern the fact that I want to generate 200 mountain names? I probably don't, but you can think of more creative use cases where I actually would want to be able to do things like govern who's going to be able to access your workflow, who's going to be able to run the models, how many times you would like them to be able to run it, just so you don't overpower your server, right? So you could use the Amazon API along with the server set up in the EC2 instance, and then you can make a REST call to KNIME Server and say, hey, give me 20 mountain names. It runs, and you get the results. So we'll see here, one more slide here. So one of the things that KNIME Server will allow you to do is it'll give you a REST API endpoint via Swagger, so you could then turn around if you have folks on your IT team and say, oh, I've got this REST API endpoint, I could build this into an application. Again, when we're thinking about mountain names, maybe it doesn't make sense to do this, but I'm sure you could think of ways where it would be useful to have an API endpoint to be able to talk to a model that's on the cloud. And then finally, the KNIME web portal. So I can actually access this workflow that I've built within a web browser, tell it to fire off the workflow, it goes to the server, and gives me the results right away in a tabular form. So let's go look at a demo of what some of this would look like. I managed to not turn my machine off this time. So the simplest way, this is the deployment workflow. Again, this is already run, and so if I wanted to look at the results on my local machine, here's one way I could do it, to just have it present for me the table of results. So there they are, right? Let's look at SageMaker right quick. So I'm going to go to my web browser. Oh, so here's the KNIME.com webpage. Here's the yellow download button that I keep telling you about. So you know that that's there. Amazon SageMaker. So I'm not a SageMaker pro by any means. Let me say that up front. In fact, somebody else on our development team put this proof of concept together, so I'm just here to explain it to you. Those of you who are more familiar with SageMaker, don't cry or be sad that I talk about this in a slightly dumb way. But what I wanted to show you here is, so we talked about this Docker container that we've packaged up our deployment workflow in. We have this as a model package. In this case, it's the Mountain Remars model package. Once I have that there, I can create an endpoint, which I've already created ahead of time, Scott Remars 2. So this is going to actually enable us to talk to the model that we've uploaded. And then finally, up here I have some notebook instances, like a create ML models instance, which is going to fire off a Jupyter notebook for me. When I open up the Jupyter notebook, this is where I could actually interact via SageMaker with the model that I have deployed. So you can see here there's just a little bit of code. All that I have to do, oh, whoops, I've already got some names down there. That's no good. Let's clear those out. Or not, because I can't all of a sudden remember how to use Jupyter notebooks. Okay, so if I wanted to generate, let's say, 20 mountain names, I just have this parameter that's being passed as JSON input. Number of new names is 20. I have to point to the correct endpoint, and that's really all I have to do. So once I execute this, then it'll sit here and think for a second and spit out my mountain names for me. He said, praying to the demo gods. Ah, there we go. So anyway, some results. Nowden Hill, Fishwall Knob, that's a new one. Salton Peak, that's pretty good. So there's some weird ones in there, but there's also some good ones. So this is the SageMaker way of doing it. Like this is kind of primitive, right? Because we just kind of whip this up, but just so you know that this is something that you could do within SageMaker. If I was going to do this using NIME Server, let me show you a couple of ways how that might actually happen. So if I go over here, I've actually got a NIME server that's spun up in AWS already. I have some IP address that I can point to, and my NIME Analytics platform knows, hey, go look for the server here. I've already uploaded, in fact, this particular workflow, O2 deployment _ AWS. So there's a few things that I could do. The first thing is I could show the API definition, and that is going to bring up for me the Swagger interface. So if you're familiar with Swagger, what this is going to do is allow me a REST API endpoint. So I could go down to execution, submit a post request. I can go down here and say, hey, try it out. When I do try it out, it's going to say how many names do you want to generate. Again, this is JSON input. It could be any number. I'll let it be 20 again. And then I go down and click execute. It's firing off the workflow and running it on NIME server, and I should get some results here shortly. So I have to scroll down to actually see them in JSON format. Here they are. So those are some really, like there's a weird Hawaiian looking one, Pu'u'u. That's kind of cool. Comptoff Mesa, we've got some in there. So there's the Swagger AI, and then, like I said, you can pass this off to your IT team. Now that we've got a Swagger endpoint, they could build this into an application and do something cool where they could actually call the model remotely. And then, well, in fact, we have a way of doing that. Like here's a simple website that one of our guys built that actually uses that REST endpoint to go out and say, hey, how many names do you want? I would like just 5 this time. Creative mountain names since 2019. I only got 4 back. The reason that I got 4 back was one of them was a repeat. So Granster Mountain, McPee Mountain, probably don't want that on our jacket, or maybe you do. So anyway, just to give you an idea of the way some of this might need, oh, one more. And then finally, I wanted to show you the web portal view. So I show you the Swagger API. If instead I go and open the web portal, then I have a way, once I log in, to actually execute this workflow via my web browser. This is entirely via my web browser. I just go over here and I say, oh, here's my O2 deployment API or AWS. Basically, all of my workflows are here, actually, if I wanted to run them. I click Start, and this is set up to generate, I think, 20 already. So I'm going to get a tabular format here of a whole bunch of them. One of the nice things about the web portal, again, not showing it here because this is a bit of a simple contrived example, but if you wanted to have multiple visualizations here, you could think of things like a parallel coordinates plot combined with a sunburst chart, combined with a tabular view and a line plot or a heat map. You could put all of this stuff to interact in a single view on the web portal and then click around and explore your data. I'm not showing that here. We have several other workflows that will do that for you, but just so you know, that's one of the advantages of using web portal is to actually build some custom dashboards. So this is how, several different options that we would have to deploy the model. Enough demo. I've got about 10 minutes here. and beer awaits. So what do we end up with? Inspiration for our poor marketing schlubs in the windowless basement who are miserable. We say, hey guys, look, what about Casterland Mountain? What about Roybal Butte? Maybe don't use Mount Crapsland, okay? But there's, here's 20 that we could give you. We could give you 20,000 if we want. It just takes a little bit longer to run. And note, this doesn't have to be mountain names. We used mountain names because it's a simple example to talk through, but we could use any kind of text to generate new text, provided that we give the correct input data set. And in fact, there's several examples of this. So we could use existing Shakespeare plays to generate new Shakespeare, or we could come up with song lyrics, or we could invent new weird baby names that you wouldn't want to use, or maybe pharmaceutical, new drug names, all sorts of stuff that we could do. And in fact, speaking of Shakespeare and lyrics, we actually have done this. So here's an example here where we took, I think it was 8 different plays, King Lear, Othello, and several others, to build a Shakespeare generator. And what you do, once you've trained the model, is then we give the user an option to provide 100 characters as a seed, and it takes those 100 characters, that's what's in red at the top there, and everything else is generated by the model. And so it's not iambic pentameter, right? It's not proper Shakespeare. It does the best it can, but it actually, if you read it out loud, it kind of sounds like Shakespeare. I found you're like a thief from the heart that purchase, whatever that is, will be well, et cetera, et cetera. But you'll notice that some things that the model does pick up on. It picks up on character names. It picks up on spacing. It'll even get things like stage directions in there, which is, it's not shown, but it can do that. Oh. That's weird. I'm missing a bit. Oh, one of my slides is supposed to show rap lyrics. That's too bad that those aren't there. Oh, we have another workflow that will generate rap lyrics. I think we use 32 different songs from the 80s and 90s. We have to be a little careful there for copyright and also because it gets kind of filthy, as you might imagine. But one of the interesting things the model will do is it will actually rhyme. And it will include parenthetical phrases where parenthetical phrases should go. LSTMs are fascinating. Once you put them into use and you see the types of things that they try to do, they're really interesting. Okay, wrap up. So enough of me talking about models and deployment and all that stuff. Like I said before, if you don't believe me, try it yourself. We're open source and free, so you don't have to take my word for it. As they used to say on Sesame Street, you can just go. You can go do it. So more links on NIME and deep learning. This talk is actually based on a full article that's available at Datanami that's published by our data science team. So more details are there. I've also got links for you for the training workflow and the deployment workflow. In fact, if you're interested in doing other stuff with NIME instead of text generation, we have a whole bunch of different workflows at the NIME Workflow Hub. So for things like image classification or churn analysis, pretty much any sort of standard data science approach, we're going to have a workflow for because we don't want you to start from scratch. We want you to start with an example in data that actually works. All that's available on our Workflow Hub. More specifically about what I've been talking about today, we have a blog post on text encoding, and then if you want to go write your own Shakespeare, you can go read that blog post and download the workflows to do that yourself too. Actually was wanting to sit down with my daughter and download some of the free Simpsons episodes and try and generate some new Simpsons stuff, just because I think that would be silly to do. Oh, and then I definitely want to point out these articles from Christopher Olah and Andre Karpathy because I use some of their graphics. They're really, really, really good. So if you want to dive into the math and the structure of how these things work, LSTMs and RNNs, those are really good articles with some excellent examples. Marketing slide here. If you are interested in learning more about NIME and you would like to meet up with some of our developers and our users, our US team is actually based in Austin, Texas. That's where I work. We have a conference in Austin every year. This year it's November 5th through 8th. First 2 days of the conference are training courses, so all the way from I've never seen NIME before up through more advanced stuff. Training courses there, and then the second 2 days are going to be where we talk about what our developers are working on. We have our end users come in and talk about some of their cool use cases. We have an early bird discount that's going on right now, but you can even get an additional 10% off of that using the Remars code that you see there. So Austin's a cool place to visit, especially in November when it's not so hot, so come see us, meet with the team. Finally, less marketing, still a little bit of marketing. If you would like some free books, I would like to give you some free books. So check out this code, REMARS0619 at NIME Press. You can get a copy of the NIME Beginner's Luck book, which is our introductory book, and then the Advanced Luck book, where we go more into things like logic and workflow variables, looping, and control. By the time, if you actually download those books and go through them, both of them, you'll be at a pretty good spot to be able to use NIME effectively. And I've gone through them myself. They're actually pretty good tools. I don't say that just because I work for NIME. They're good books. So thank you very much for hanging out. I know it's time for beer, so I don't blame you if you need to go get one. But I do have a few minutes for questions if anybody has questions.